Positron emission tomography, PET, is a nuclear medicine imaging technique. PET visualizes metabolic activity within the body, revealing organ and tissue function. Unlike structural imaging like CT or MRI, PET scans show physiological processes. PET scans are often combined with CT or MRI for precise diagnoses. Hybrid modalities such as PET-CT or PET-MRI provide comprehensive diagnostic information. PET scans utilize positron emission and annihilation radiation principles for medical imaging. A radioactive tracer, typically FDG, fluorodeoxyglucose, is introduced into the patient's body. FDG is a glucose molecule labeled with the positron-emitting isotope fluorine-18. Cancer cells consume more glucose than normal cells, leading to increased tracer accumulation in cancerous tissues. The accumulation of the radioactive tracer in cancerous tissues is a key factor in PET scan imaging. Positron emission from the tracer allows for the detection and localization of cancerous tissues. Fluorine-18 undergoes beta plus decay, emitting a positron. A positron is an anti-electron, possessing the same mass but opposite charge. The emitted positron travels a short distance before colliding with a nearby electron. Upon collision, the positron and electron annihilate each other. The annihilation of a positron and electron produces 2 gamma photons. Each gamma photon has an energy of 511 keV and travels in nearly opposite directions, approximately 180 degrees apart. A PET scanner utilizes a ring of detectors to capture radiation emitted from the patient's body. The detectors consist of scintillation crystals coupled with photomultiplier tubes. The detectors simultaneously detect 2 gamma rays, a process known as coincidence detection. Each simultaneous detection event maps a line of response, and millions of these events are collected during a scan. Data from coincidence detection events is processed using computer algorithms to reconstruct a 3D map. Filtered back projection and iterative reconstruction are examples of algorithms used in the image reconstruction process. The 3D map represents the distribution of a tracer within the body. This tracer distribution map reflects the metabolic activity of tissues and organs. Areas of increased or decreased activity are identified through the reconstructed 3D map. The reconstructed image aids in identifying areas of increased or decreased metabolic activity. PET scans are used in oncology to detect cancers, metastasis, and assess treatment response. In neurology, PET scans aid in studying Alzheimer's, epilepsy, Parkinson's, and brain activity. Cardiologically, PET scans assess blood flow and heart muscle viability. PET scans involve low doses of radioactive isotopes that decay quickly, keeping radiation exposure within safe medical limits.